Hello and welcome back. Yesterday we spent most of the day talking about the idea of effusion and diffusion, the way that gases spread out. And it was all idea-based. Today we're going to talk about Graham's law, which is the mathematical model that we can use to take those ideas and apply them to chemistry. It's our second to last gas law, and being direct, Graham's law can get pretty tricky pretty fast, so we're not going to actually end up doing a worksheet over Graham's law. And instead we're just going to deal with it together here in this context. So Graham's law is going to deal with saying, using math, how do mixtures of gases spread? Now we know a little bit about this as an idea, but how can we actually predict the exact locations? And if you're like, whatever, this doesn't matter, this kind of question underlies so much of practical engineering. Now, let's think about this for a moment. Let's look at two gases. We have ammonia and hydrochloric acid, NH3 and HCl. And I've given their molar masses. And looking at yesterday, we knew that one of these would move faster than the other. Which one would move more quickly? Which one would diffuse faster? And so we know the lighter one is going to move faster. And so that means over a given amount of time, ammonia will travel farther than HCl. Now, these two chemicals are both extremely common in a chemistry lab, and you've worked with both multiple times. And normally we would go to a lab to show you these two things reacting. And we'll do that today just by video. But to know the reaction between these two things, you have to understand there's a little bit of a surprise. And it's this, that gaseous ammonia and gaseous HCl make NH4Cl S. What's that S stand for again? And so this is going to make a solid. Now, HCl is effectively clear and NH3 is effectively clear. Both can have some effect on the water in the atmosphere and make little condensation clouds. But they're basically two clear gases that meet and make a solid. It's not a precipitate, it's even more. And so this reaction is really interesting. Let's cut over to some footage from the Backyard Scientist, a YouTuber, to show the reaction before we do it in a more confined way. So here you can see two beakers, the ammonia on the left and the HCl on the right. And even with a watch glass over the top, the ambient vapors are reacting a little bit, smoking, right? But as soon as he comes and removes that watch glass, you get a much more obvious reaction. And that white smoke there is actually ammonium chloride. It's a solid. It's just a very fine particle. It's not heavy enough to fall out of the air. You can see as he moves the two beakers closer together, they react more vigorously. And as he moves and mixes them, you get a reaction over both. So the HCl and the NH3 here are reacting in the air without the liquids touching. Just the vapors are what cause the reaction. All right, so let's talk a little bit about what we're going to use that reaction to actually demonstrate, to actually see happening. And that's Graham's law. So this is the mathematical model that we're actually going to use today. And it looks a little scary, but it's not too bad. Let's start off over here on the ending side. We have a square root of a fraction of the molar mass of B over the molar mass of A. So these are molar masses, so what units do they have to be in? All right, so this ratio over here, just a number, right, is equal to a second fraction, which is the rate of one divided by the rate of the other. So our two gases, A and B, and their molar masses in grams per mole are going to be determined. Now, this in itself is pretty useful, and this is the form I'm going to show you in the video today. In real life, it's probably a little more useful to write it this way, that delta x over delta t. Delta is a Greek letter in math used to represent the what? So the distance my first gas will go over a certain amount of time divided by the distance the other gas will go over a certain amount of time. So if I could come up with a way of measuring how far that gas goes and keep the time that both gases are allowed to travel constant, then the only thing that would determine where they met was their molar masses. It's a very elegant thing. So if I know which gas is heavier and which gas is lighter, I can know which one's going to go farther over a certain amount of time. So let's make a prediction. We know that ammonia has this molar mass, and that hydrochloric acid, or really hydrogen chloride, the gas that it's going to make, has this molar mass. So if we know that the lighter gas effuses faster, has a faster rate, then which chemical has to be going farther in this particular reaction? Now, scientists like to play a trick when it comes to rates. Rates are a distance over some time, and we can control the time. We can make the amount of time equal to 1. And we can play an even bigger trick. If we define the slower rate as 1, then this math gets pretty easier. So for this class, and for how I'm teaching you how to do Graham's law, and for most of real life, whichever rate is slower, we're just going to call 1. And we already know which rate is going to be slower, because we know whichever thing's molar mass is heavier, because molar masses are very easy to find. So whichever heavier mass, let's say B, because it would be the easier one to do, let's put the heavier one here and always make this number 1, then this term actually goes away and you just get rate A equals this ratio here. So the math gets pretty easy. Let's actually take a look at it together here for just a moment. Let me clear my desk up. So let's look at Graham's law and try to prove it experimentally. Let's try to prove that this thing actually happens and that this pretty simple statement is actually true. And we can do that using the reaction we just talked about between ammonia and hydrochloric acid. Now we've already said the ammonia should travel farther than the hydrochloric acid per second. Its rate should be faster because it's lighter. So let's assume you've got some ammonia here and some hydrochloric acid here, right? And you put them both in the tube at the same time. Then the ammonia would come forward until they met, and then you'd get that white smoke forming where they interact, right? If that makes sense, then what we need to do is figure out, if we put them in the tube at the exact same time, where that point would be where they mix. That's a little bit of math, so let's knock it out. Now, we already said that the heavier rate can be defined as 1. So we could rewrite this Graham's law equation in a simpler form, which is the rate of the lighter gas divided by 1 is equal to the square root of the heavier gas divided by the lighter gas. So if I use that and this information here, and I put an x in for this, I should be able to solve the equation. So let's knock that out really fast. Right, so I set up the equation just using this tool. Pretty straightforward, just a plug and a chug. And now I just need to simplify this. This is all real numbers. There's no variables in here, so I can make this all into one number. And with that, I can take this number, and I know that x equals 1.463. Now maybe that doesn't make perfect sense yet, what that number actually represents. So let's draw a quick picture. 1 second. All right, I think this makes pretty good sense. Let's say you put both things inside a glass tube, and you put them in at exactly the same time. Then our prediction using this math is the HCl would travel forward a distance of 1 in the time the NH3 went forward a distance of 1.46. So we'd predict the white smoke would form farther away from the NH3 and about 1.5 times the distance it would be from the HCl. That sounds like something we could go test. So let's head over to a laboratory and watch a couple videos of this reaction and see how we did. So I'm going to use this college video here to actually demonstrate what's going on and let you see it as a college student would.
We have a tube that is approximately 1 meter long. On one end, we're placing a cotton ball moistened with concentrated ammonia. On the other end, we've placed a cotton ball moistened with concentrated hydrochloric acid.
Now, as we look at this, the cotton ball is in a pretty big hole, right? The tube is bigger than the source of gas. So is this effusion or diffusion? You might also notice that the diffusion takes a while. And that's because the gases that are being released in the tube from the ammonia and the HCl are still hitting into the air molecules already in the tube. We talked about that yesterday, that diffusion takes time because you've got to knock all those air molecules out of the way randomly. And to me, it looks like this has been sped up 2 times, but you can see that ring starting to form right there at apparently about 45 centimeters. So you can see that little ring of ammonium chloride forming up there, and the solid depositing along the bottom. So there we have some data. Let's work with that. So here are my notes from the video. I thought that the HCl was located around 2 centimeters and that the NH4 was located around 94 centimeters. I saw the ring forming at 45 centimeters, which means the distance from here to here was 43 centimeters. And let's see, 45 to 94 would make this 49 centimeters. So right off the bat, I do see the ring is farther away from the ammonia than it is from the hydrogen chloride, but that doesn't look like 1.46. As a matter of fact, if I take my calculator here really fast, 49 divided by 43, yeah, it's 1.13. This was a pretty something result. So what do you think? Do you think this alone proves what we're trying to show? So I would argue this is a bad result. I mean, let's talk about percent error really fast here. Something like 25%, right? And I don't know. I feel like there's probably a better video out there than this. Let's go try another one.
Into the right-hand side.
All right, here's another video.
We put some cotton wool that's soaked with concentrated hydrochloric acid. And into the left-hand side of the tube, we put some cotton wool that's soaked with concentrated ammonia.
Well, this experiment's garbage. What's wrong with it? Why can't I use this for data? Still, you can see the ring is closer to the HCl than the NH3, so it does prove our overall idea, but we can't check the math with this. How hard should it be to actually find a video of this reaction carried out by someone competent? Like, the first one had so much promise. It had a meter stick. Well, let's go back to YouTube. Let's see if we can't find someone who knows what they're doing. I have such high hopes with the Darude sandstorm in the background. Total garbage. And I'll probably get a copyright strike. Great.
So this is ammonia solution. The reason why you see when I started to open, the fumes have started. That's why I've had a redone what? I covered it.
So this is definitely Rwanda or Uganda. I can just tell by the classroom. Like when I taught there, it just looks like that part of the world. Can't tell you exactly why. So he's got the ammonia there, and I have like legitimately high hopes. A lot of the teachers in this part of the world are phenomenal. And oh, he almost made the mistake, but he pulled it away. Hold on, we have a chance. Hey, not bad. Never mind. Well, let's still watch the experiment out.
Now I want you to come and see where you can see like something like where there is a cloud. There is the white fumes where they are.
Well, it doesn't work for us, but still kind of cool to see and a nice throwback for me. But we gotta find another video, so here we go.
Oh, come on, chemists. Today,
Oh yeah,
we're
this
showing
guy's
you a
good.
demonstration
He already
of
disdains his
Graham's
students and is
law.
condescending.
That
I'm
means
liking
commonly.
it.
I don't care about
Set
my
up
skill.
though.
Okay, Mr. Moore, tell me when you're ready here.
We'll be ready. Students, are you ready?
Okay, here we go. Gas is in.
Hallelujah.
Actually, my fingers are burning a little bit. I'm going to go rinse my fingers off while we're waiting.
Weak.
So it looks like the HCl went, what do you think, Mr. Moore? 25 and a half, do you want to call it?
Looked like it, yeah.
About 25 and a half centimeters. And if I go right from the end of the tube, what do we have? 30, maybe 36 and a half?
Well, that was a marathon. I probably could have driven to Rockhurst faster and recorded my own good experiment before I found one, but I can't get in, so here we are. Here's their data, though, and this data looks pretty good at first glance. Their experimental procedure seemed pretty valid to me, and yeah, we look pretty good. So all we have to do is divide those two numbers. Okay, 36.5 divided by 25.5 gives 1.43. And that should be a holy crap moment for you. After all, we predicted 1.46. And here we are with, hey, that looks really good. But I want to point out, I had to go through a lot of videos. I probably watched 10 or 15 videos before I found one where the experiment was carried out in such a way where it would prove it. And I want to make the point that actually doing this experiment and proving this and finding that, yes, the thing that's going on is really and truly Graham's law wasn't easy. Gases are hard. This took Graham, Thomas Graham being the chemist, a long time, most of his life. But once you figure it out, yeah, I can show you it pretty easily. It works. Again, I'm not so concerned with you being able to do this math or understand how like delta X, delta T plays into it this year. But if you see, wait a minute, I was able to predict this and get it right and see the kind of beauty of that, then it's great. Now, there's a less traditional form of this experiment using an indicator because ammonia is a base and HCl is an acid. And so, like, my indicator will turn colors in the presence of them. And I think it's actually a lot cooler because you can actually see the different diffusion rates meeting at the middle. So let's go ahead and watch that experiment really fast.
Another way of monitoring the progress of the gases is to run a piece of damp indicator paper along the tube. Hydrogen chloride gas turns it red. Ammonia turns it blue. Why does ammonia travel faster?
So I took a screenshot of that video and I can actually perform my measurements here just using like a photo editing program. So let me speed that up for you. Alright, so that gives us two numbers there. And very quickly typing those into my calculator, which I know you can't see. Actually, one second. Gives us a result that looks pretty awful. Right? We were so good on the other one, and here this indicator's not great. And the problem here is that the experiment was allowed to run way longer. As a matter of fact, if you were to go back a little bit in the video, you'd see something else.
Place the two pieces of cotton wool at opposite ends of a tube and the gases spread out. You can compare the speed at which they approach each other by looking out for a cloud of ammonium chloride. After less than a minute, a white ring begins to form, marking where the gases meet. The white solid is closer to the hydrogen chloride end of the tube, on the right. So which gas has travelled faster?
So here we go again. Hey, will you look at that? Not bad. Again, remember what we originally predicted. Hey, go back to my desk really fast. Remember, we just got 1.44, and now we're predicting 1.46. So finally, we do get results that seem to prove this is true. but they're a mess. And the math can get a lot worse. And so for this weekend, you don't have anything else. This was meant to be kind of like a lab would be, to show you, hey, this actually does exist. It is real if you're careful enough and do the experiment enough to prove it. So for now, have a wonderful weekend, and I'll see you on Monday. Buen camino en todo.